Welcome back to my channel. This is part 5 of our Introduction to Calculus series, and today we're exploring derivatives. Let's get started. Let's consider the following equation, and let's calculate the slope between 2 and 8. The slope is the ratio of the change in y and the change in x. But how to find a slope at a point? For example, at point 2, it can't be 0 over 0, right? For that, we need a tool called derivative, which uses small differences and shrinks them towards 0. We should come closer to the point 2 to see that. We are calculating the very small change in y related to x. This is the slope of the tangent at point 2. Let's call the specific point x0 and replace y by the function f at that specific point. We want to find the change from x0 to a nearby point. Rename the horizontal change as the increment h and apply the limit as this step shrinks to 0. Finally, we have the formula to calculate the derivative of the function f at a specific point x0. We call it f prime of x0, and this formula can also be called as the difference quotient. We can now find the derivative of our function. Start by filling in the difference quotient. Simplify it. And finally, apply the limit as h shrinks towards 0. The result is the derivative of this function. You can also use this notation instead of f prime. This result means that the slope of the tangent line at any point on fx equals the derivative at that point. It can also tell you the rate of change at that point. See this point as example. The slope of the tangent in x2 is 0.8. If you relate this to the equation of the tangent line, then you have the following. This also means that the rate of change in 2 is 0.8. Don't forget, we are talking about very small changes. So in fact, this is the instantaneous rate of change. For example, when you change x from 2 to 2.001, you are increasing 0.8 times the displacement in the y-axis. From this derivative, you can conclude that the derivative of x squared is 2x. And you can make your calculations to see that the derivative of x cubed is 3x squared, and x to the 4th is 4x cubed. Therefore, we can consider the following rule for the exponentiation. Remember, this rule works for roots too. Just rewrite them as fractions first, then apply the rule, and simplify it. If you plug in n equals 1, you'll find the derivative of x is 1, which you can also easily get using the difference quotient. What if it's 2x, 3x, 100x, or 2000x? Basically, x times some constant c? Then the derivative is just that constant. Can you guess the derivative of the constant c? If the function is constant, nothing changes, right? Then, what is the rate of change? It's always 0, which can also be proved through the difference quotient. We've looked at x raised to a power, but what if x is the power? That one's trickier to prove and really needs its own video. So, for now, let's just go with the result. Be careful though. This only applies when the constant is greater than 0. The reason? The inverse of the natural log, which is the exponential function, only produces positive numbers, as I have explained in one of my previous videos. Replace a by the Euler number. What is the natural log of Euler's? 1. So, the derivative of this function is the function itself. That's just one of the cool and unique things about this number. Here's the derivative of the natural log. Another tricky one to explain in this video. Once again, this only applies when x is greater than 0, and the reason is the same. Below are the derivatives of several trigonometric functions, which you can work out using the derivative formula and some trig properties. Who knows, it could be a future tutorial. So, what are derivatives for? They have many uses, but let's focus on the most visible ones, using coordinate graphs. Derivatives can help us find local maxima, local minima, and stationary inflection points of a function. A local maximum is a point where the function reaches a peak in a small neighborhood. In other words, the function increases before the point and decreases after it. If you're climbing a hill, the top of the hill is a local maximum. A local minimum is a point where the function reaches a low point in a small neighborhood. The function decreases before the point and increases after it. If you're walking through a valley, the bottom of the valley is a local minimum. A stationary inflection point is a point on a curve where the concavity changes horizontally. The surface curves up in one direction and down in another. If you're climbing downhill or uphill, is where you can rest because it's a small plane. Where is it flat? Where the slope is 0. Where is the slope 0? Where the derivative is 0. Ready to climb our mountain? This function shows how long it takes to go up and down. The horizontal line is the travel time, and the vertical one shows how high you are at each moment. How long does it take to reach the top? And how high is it? First, use the derivative to find the slope of this function. You can use this notation for the derivative. You want to know the rate of change of height with respect to time. The derivative of a constant is 0. If you multiply a constant by a variable, the derivative is just the constant times the derivative of the variable. It's a basic rule. We'll learn more about it later. For now, just leave the constant as it is. Just treat whatever's inside the parentheses as x. The derivative of x squared is 2x, so it's 2 times whatever is in the parentheses. Next step. Simplify this. It's just basic algebra, so I won't go into details. Now that you've got the derivative, find out when the slope hits 0. This means you reach the top of the mountain after 120 minutes, that is, 2 hours. And what is the height? Just replace the time in the original function. The result is 300 meters. We can see in the graph that it's a maximum, but can we prove it with math? For that, we need the second derivative. It's just the derivative of the derivative. Sounds confusing? Let's start with the notation. You can use one of these common forms, h double prime, or second derivative h with respect to time. Then, take the first derivative of the function and find its derivative again. The derivative of a constant is 0. The derivative of a constant times the variable is the constant itself. The result is a negative value. This means the slope decreases as the function progresses. It starts positive and decreasing while going up, reaches 0 at the peak, and increases negatively as it goes down. That's how we know it's a local maximum. Let's try a more complex function. But first, let's clear out these derivatives we don't need and make some room. Now, calculate the derivative. The formula is always the same for each power. Next, find where it's 0. I'll show the answers, but feel free to do the calculations yourself. Then, the second derivative. Once again, we use the same formula. Since we have more than one solution, we should plug each one into this equation. Let's begin with 1.17. The result is a positive number. Therefore, this is a local minimum. Now with minus 0.77. In this case, this is a local maximum, because the result is negative. When x is 0, it's easy to see the result is also 0. The second derivative is positive when the curve bends upward. Values go up and down until they hit 0 at the inflection point. After that, the curve bends downward and the second derivative becomes negative. That's how we know this is an inflection point. And since the first derivative is also 0, it is a stationary inflection point. But wait, we can see from the graph that there are two more inflection points. The slope isn't 0 there. So how do we find them using math? We need to solve where the second derivative equals 0. Let's skip the calculations and go straight to the solutions. We already knew that x equals 0 because it can be calculated using the first derivative. As for the other 2 points, we need to use this method. So in summary, the first derivative equal to 0 gives us critical points. The sign of the second derivative tells us whether we have a local maximum or a local minimum. An inflection point occurs when the second derivative is equal to 0 and the concavity changes. If the first derivative is 0 at that point, the inflection point is stationary. If it's not 0, then it's a regular inflection point. And that's it for today's lesson on derivatives. We have covered some of the fundamental rules, but in the next video, we'll explore them in much more depth. If you've learned something new today, make sure to like the video and subscribe. I'll see you in the next video.